Hello, welcome to another math counts meeting. Today, Austin isn't available right now, but he will be joining us later. So today we're going to be continuing 2011 National Sprint. So let's start on problem 22. Circle O has radius 10 units. Point P is on radius OQ and OP equals 6 units. How many different chords containing P, including the diameter, have integer length? Okay, so let's copy this graph, I guess. Okay, so we have here, so it says circle has radius 10, so OQ is 10. Q is 10. And point P is on radius OQ, and OP equals 6, so this is 4. And so if we extend this is 10. So that's 6. This is 16. How many different chords containing P, including diameter, have integer length? So first thing, when you see this kind of problem, you might be thinking of like power of a point, because you have two chords and you're dealing with chords and you're given the length of this chord on each side of P. So just think about it as power of point first. So 16 and the other side is 4. So that's 64. So each chord on each side of P has to multiply to 64, and we're looking for integer length. So first of all, 64, if we think about it, 64 is 8 squared. And for both sides of the chord to have the same length, it must be perpendicular. The diameter has to bisect the chord, and when diameter bisects the chord, it's also perpendicular. That's just a property of the circle. So we are left with 8 and 8. So this chord has a length of 16, so that's integer, and so that's what we're looking for. So now let's think about the length of the chord. So let's think about the length of the chord as we rotate the chord around P. So like the chord here, here. We're just going to think about how they're rotating counterclockwise from the diameter right now. We'll think about the other way later. So like this. So as this happens, the length of the line, it goes from 20 to 16, and it's strictly decreasing. So from 20 to 16, and it's strictly decreasing, which means if we're looking for the length of the chords that includes we're looking for the length of the chords that are integer length, it will be 20, 19, 18, 17, and 16. So now that's one side. Now if we think about the other side, it will just be a chord like this, this, and this, and so on, right? It's basically the same thing but mirrored over. But 16 and 20, they're symmetrical. They're like, if you do it to the other side, it's the same line. So we don't do 16 and 20. It's just 17, 18, and 19 again. So we end up with 8 chords. And yep, that is our answer, 8. So number 23. Number 23. In 2010, the probability of Mark sinking a free throw was twice what it was in 2009. Yet the probability of him thinking exactly 2 out of 3 free throws was the same in both years. What is the probability of Mark sinking a free throw in 2010, given that the probability was greater than 0? Express your answer as common fraction. Okay, so let's write down what the probability of him sinking 2 out of 3 free throws is. It will be, let's say, the original, make this less pixelated. Let's say the original probability was P naught. So it would have been, actually we can just say it was P, because we can represent the other one. So we'll say the original probability is P. So the probability of him sinking exactly 2 out of 3 free throws in 2009 will be P squared times 1 minus P. And we can set this equal to, his probability in 2010 will be 2P. So it would have been 2P squared minus times 1 minus 2P. So we can just like, so we can just like expand this, right? We end up with like P squared minus P cubed equals 4P squared minus 8P cubed. And we can take a P squared out of all these. So 1 minus P equals 4 minus 8P. Yeah, 1 minus P equals 4 minus 8P. So switch over, we get we get 7P equals 3. P equals 3/7. The probability will be 3/7. Oh, 6/7. So I got that wrong. Huh. Okay. Let's see here. 4P squared. P squared 1 minus P. So P squared minus P cubed equals 4P squared. Oops, my bad. So 4P squared minus 8P cubed. Hello, Austin.
Okay, sorry for yeah, I forgot that I need to let you into the meet. Or I mean it wouldn't have worked out anyway, right? We because then, you can't let other people in. But
Oh yeah, that's a
yeah.
good point.
Uh well, I don't think anyone joined anyway, so it's not that.
Yeah, yeah.
Okay. Yeah, I'm sorry, yeah, I had to have dinner.
Okay,
Sorry,
fine.
I am
It's fine.
late.
Okay, so since P is the probability in 2009 and P equals 3/7, we're looking for the probability of Mark making a free throw in 2010 over 2P, and so that equals 6/7. And so, yep, that's our answer. Okay, number 24. Boxes are arranged in a 20-layer tower. The top layer has 3 boxes, and each subsequent layer has one more than twice the number of boxes in the layer above it. If 2 to the power of n is the largest power of 2 that is a factor of the total number of boxes, what is the value of n? Okay, so let's think about it for a second. So if the top layer has 3 boxes, the next layer twice has one more than twice the number of boxes in the layer above it. So like it will be 2 times 3 plus 1, it'll be 7. And the next one will be 15. And the next one will be 31. So you might notice a pattern here, which is this is 4 minus 1, this is 8 minus 1, this is 16 minus 1, this is 32 minus 1. And these are just powers of 2, right? 2 to the 3 minus 1, 2 to the 4 minus 1, 2 to the 5 minus 1. And this can be proven and this pattern continues, and like this can be proven because if you think about it, 3 is 2 plus 1. So if you multiple, so if we like, if we substitute, if we substitute like 2, like if we substitute x for 2, x plus 1, and then we're just multiplying by x plus 1, we end up with x squared plus x plus 1. And if we multiply this by x and then plus 1 again, it just continues, x3 plus x squared plus x plus 1. And these are equal to x to the 4 minus 1. So if we put like 2 back in there, this is like x squared.
Do
X
you wanna
minus 1. Sorry, what?
show how it equals x to the 4 minus 1? Or I
Oh,
mean, isn't that only with if x is equal to 2?
I'm pretty sure that's with x equals to all of them. Because think about it, if you put it in like
Or
base.
if you had like
Mhm.
3 plus 1, you're saying that is 3 squared minus 1, right?
Oh, yeah, sorry, my bad. It's only base 2. Wait, it's only base 2. Oh, wow.
Yeah.
Oh, sorry, that's
Or
my
so
bad.
like I mean, like x to the 4 minus 1, it's equal to x minus 1 times like x cubed plus x squared plus blah blah blah, right?
Okay.
And if x is 2, then the 2 minus 1 is just 1.
Oh,
So
shoot.
then it's just the
Okay.
rest of.
For some reason, I've always thought it was just like for all x's. Sorry, that's my bad. And then the next one will be 2. Just 2, 4 minus 1. So this pattern will continue. So if we go all the way to 2 to the 20th layer, that will be the first layer, it's the second layer. If we go all the way to the 20th layer, we'll end up with 2 to the 21st minus 1. So now we just want to add up all of these. And we actually use this property again when we add them up because think about it, we're adding up 2 to the, if we add up all the powers of 2 first, it will be 2 plus 2 to the 2 squared plus 2 to the 3 plus 2 to the 4 plus dot 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 2 to the 21 minus 20. So we use that property again, and this will be 2 to the 22nd minus 1, but we also have to minus the, what would have been a 2 and a 1 here, but we don't have these, so we have to minus another 3. So minus 20, we end up with 2 to the 22 minus 24. So the largest power of 2 to be a factor in this number, for that power of 2 to be a factor of this number, it would have to be a factor of both of these. So this is 2. 24 is 2 cubed times 3, and 2 to the 22 is 2 to the 22. So the largest power of 2 that can go in these is 2 cubed or just 8. And so, yep. Oh, the value of n, 2 to the power of n. So it would just be 3.
Yeah.
It would just be 3.
Okay.
So,
But yeah, so the property where you have like, 1 plus 2 to the first plus 2 squared plus dot 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 like to 2 to the n. The property that equals like 2 to the n plus 1 minus 1 uh is like pretty important. Like it shows up a lot in like um competition math, I guess. And if you're wondering how like um you can derive it, well, one thing is that you can think of it in binary, right? So, if you have like 1 plus 2, 1 which is just 2 to the 0 plus 2 to the first plus 2 squared and so on, it's like in binary you have like 1 for each of those positions because like each like 2 power is like um a place value. And then when you have like 2 to the n plus 1, that's just like you have like just a 1 in that place, and you have zeros all like afterward, right? And then when you subtract a 1 from it, then you have to subtract or like if you subtract 1 from like a 1 0 0 0 0 0, it's gonna become like 1 1 1 1 1 1 with a length that is 1 smaller, right? So then you can see that you know the property can be proved in that way. Um, you can also prove it in like the factoring like way where you can generalize it to like x. Bill, do you think you write like 1 plus 1 plus x squared plus dot 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 all the way to like x to the n. Okay, so this will equal x to the n plus 1 minus 1 all over x minus 1.
Sorry, can you say that again?
It'll equal, I mean, so you should put the 1 plus stuff, put that in parentheses and multiply that by x minus 1. No, one just all of it, yeah.
Multiply this whole thing?
Yeah, and multiply it by x minus 1, and it equals x to the n plus 1 minus 1.
Oh, right. Yep.
You should put an equal sign. Yeah. Okay, or yeah, okay. Okay, and then so just think about like how this will hold first. So like if you think about expanding the x minus 1 into you know the big thing on the left, if you first multiply the x by the x to the n, you see that we get our x to the n plus 1 value. And then if we multiply the x by sorry, by x to the n minus 1, the one lower term, then x to the n, then we will get x to the n. But you see that when we multiply the -1 times the x to the n, we're going to get minus x to the n. So when we multiply x times x to the n minus 1, we're going to get x to the n. We multiply -1 by x to the n, we're going to get negative x to the n. And so those two terms will cancel out. And then you see if we move like one term lower, we're going to multiply x times x to the n minus 2, which will give us x to the n minus 1. And then if we multiply the -1 times the x to the n minus 1, we're also going to get negative x to the n minus 1. So those two terms will cancel. So you can see that if we take pairs of terms like that, they're always going to cancel. But with like the -1 multiplying like one term above the x, right? So we're going to keep on going like that down, except our initial term of x to the n plus 1, that was never canceled, right? Because, you know, the -1 can't multiply by an x to the n plus 1 to cancel that out. But anyway, so we're going to move that down. We're keeping on like canceling terms. And then, you know, once we get to the end, the x term is going to cancel out, right? Because the x is going to be multiplying by the 1, that gives you x, and the -1 multiplies by the x, and that gives you negative x. And then those two terms will cancel out. But then, you know, then the x is done, right? It's multiplied by the whole thing, but the -1 is not done yet, right? It hasn't multiplied by the 1 yet. So then the -1 multiplies by the 1, and then you get your last term that doesn't cancel out, which is -1. So then you can see that the whole whole expression will equal x to the n plus 1 minus 1. So this is a generally a pretty important factorization to know. I don't know, it comes up like decently, like if you have like, you know, some, you know, terms that are like this, you know, maybe you can like factor it or something. But yeah, but this can also prove our like lemma thing that we used, which was like, you know, 1 plus 2 plus 2 squared plus dot 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 all the way to 2 to the n, because in that case x would equal 2, right? And then, you know, you can see that the x minus 1 term, that will just be 2 minus 1, which is just 1, so it's just going to cancel out. So then you can see then we just have like the thing that we were trying to prove before. But yeah, so that stuff is pretty important, I guess. Just, you know, if you don't know it, look at it a bit. But yeah, that's, I guess, the takeaways from this problem.
Okay. So, let's go to question 25, I guess. Oh, shoot. Fine with it. Okay. Question 25. Each number in the set 5, 9, 10, 13, 14, 18, 20, 21, 25, 29 was formed by adding two of the numbers in the set A, B, C, D, E, where A is less than B, less than C, less than D, less than E. What is the value of C? Okay. So we have 5, 9, 10, 13, 14, 18. I should write these smaller. 5, 9, 10, 13, 14, 18, 20, 21, 25, 29. Okay, so a couple of things we can see just right off the bat. 5 has to be A plus B because it's the smallest. 29 has to be D plus E. And A plus C would have to be the second smallest because B plus C is greater would be greater than A plus C. So, and with the same thing, we can see that C plus E equals 25. Okay, so now we have we're left with the numbers in the middle. So we can think of them. Okay, so 10. So for 10, 10 can either be A plus D or B plus C. Because these two we don't know like whether they're bigger to each other or not. And similarly, 21 is either B plus
Yeah,
C
so
or C plus D. Yeah. Mhm.
so we know B plus C and A plus D is obviously bigger than A plus C, right? So like, we know B is bigger than A and we know D is bigger than C. Or so that is why A plus C is 9. But so comparing like A plus D and B plus C, we don't know, like not just by looking at it here, we don't know which one is bigger, right? Because, well, we know B is bigger than A, but D is bigger than C. We don't know how much each of those is bigger than one another, so we can't put it directly anywhere yet. But if you look at any other term, like A plus E or B plus D, those terms are like definitively bigger than either of these terms if you look at every other term. So, that means then we only have two terms like competing for the lowest spot that is not like A plus B or A plus C. So then either of those two has to equal 10. So I guess like, that's important to know. That can help us out in the future. And if you also apply that to 21, then you also have B plus C and C plus D.
Yep. Um. Right. So. Uh. Okay. So A plus D and B plus C. These two go to these two, and 20 and 21. These two will go to these two, and these two in the middle. These two will be B plus D or A plus E. We can prove that like B plus D is greater than both A plus D and B plus C because D is greater than C, B is greater than A, and likewise for this. Um, but yeah. So now, what we can do is we can look at the parities of A and B, of A, B, C, D, and E. So Austin, I think you did this part actually for the parity thing.
Sure, I can talk about it.
Okay.
Um, so okay, one thing we can do here. So, what we need to do right now is differentiate, like our pairs, right? So we have like pairs of numbers. We know that they correspond to either of two terms, but we don't know which term it corresponds to. We need to somehow like, find which one it corresponds to. Um, if you look at the pairs of numbers, some of them are not the same parity, like 10 and 13. So we can try to use parity to solve this, right? Because if we find that like A plus D parity um is like has to be odd or something, then we automatically know that it's 13 and we get a lot of information from that. Um so then yeah, we can try like maybe finding some parity information about our numbers. So how are you going to do that though? Well, we've already figured out like what four of our terms correspond to, right? And we know what the parities of those terms are. So we're gonna try to, do some stuff with that. So we know that A plus B is gonna have to equal odd, right? So you can just write that down, Bill. So A plus B is gonna be odd. Um, or I just put O just to make everything quicker.
That works.
Um,
Yeah.
yeah.
Oh.
And then we know A plus C is also O. We know C plus E is O, and D plus E is also O. Okay, so um, what we we can't figure out the exact, like we have to start by assuming one term's parity. So like let's say we start by assuming A is odd. So if we do that, then we can say that B is even because of the first thing, C is even because of the second thing. And then if C is even, then we know E is odd from the third thing, and then D will have to be even from the last thing, right? So that was if we assumed A was odd. But what if we assume A was even, right? That can be another case. So if A is even, then B will have to be odd, and C will have to be odd as well. And then from C plus E is odd, then E will have to be even, and then because E is even, and from the last thing, then D will have to be odd. So you can see that depending on um what like basically we have two possible cases of this, and they're flips of each other, but we can't necessarily say one or the other yet. But this can still help us. This can still help us because if you look at both cases, if we try to look at like the parities of our sums now, like A plus D, you can see that in both cases we have an odd plus an even for A and D. So from that, then we know that A plus D will have to be odd no matter what, right? And if A plus D is odd no matter what, and we know that it's either 10 or 13, then we know directly from that A plus D has to equal 13. And then likewise, B plus C will have to equal 10. You can also see that in either parity case, B plus C will have to be an even number. So from that, you can find those pairs. And we only needed to find like, one more pair to solve the entire problem, right? Because we just need 5 pairs so that we have 5 equations with 5 variables, right? So now, you can just take 5 of these equations and you can solve the whole thing.
Okay.
Um,
So I would like to
okay.
add something. So at this point, you can actually see that. Okay. So if we just look at this part, if we just look at the top two, just look at the top two here. A plus B equals odd. A plus C equals odd, which means, so for the top, one of these would have to be odd, right? One of these is odd, one of these is even. So if B was odd, then C would have to be odd because A is even. And if B was even, then C would also have to be even because A would be odd. So you can see that B and C have the same parity. So when you add them, they'll always be an even number. So B plus C would have to be 10. B
Yeah.
plus
I
C.
mean,
So at this point,
that's basically, yeah.
at
I
this
mean, that
point, we
that's
actually,
basically what we, sorry.
okay, no, go ahead.
That's basically what we did with like listing out like the whole case thing, but like I don't know. You can just like look at that like a little bit quicker. You're only looking at the first two, but like looking at the whole case is also basically just doing the same. But yeah,
Also,
okay.
if we only look at B plus C, then at this point we only have A, B, and C. So this is only a three variable equation instead of a five. We can solve it like this. We can just solve this like uh, A plus B equals 5, A plus C equals 9, B plus C equals 10. So we can solve this like I'm just gonna add them. I'm just gonna add all of them. That'll be 2A plus B plus C equals 24. A plus B plus C equals 12. And then you subtract this from this, C equals 7. So we're looking for C, and C is 7. And that's our answer, 7. Yay. Okay, number 28. If the degree measure of an arc of a circle is increased by 20% and the radius of the circle is increased by 25%, by what percentage does the length of the arc increase?
Wait, did you skip like a lot of questions?
Oh, shoot, I did. I'm sorry. I skipped one question.
No, you skipped two, right?
No, we just did number
What?
25. Oh, I did skip two questions. My bad. Number 26. The formula for the area of any rectangle with a perimeter of 20 units can be written as A equals n minus nd squared, where d is the length of the diagonal and m and d are constants. What is the value of the product mn? Okay, so let's just think of a rectangle. So if we look at the diagonal like this, oops, so, oh my goodness, there you go. So we're trying to represent the area of the rectangle in terms of the diagonal. So the area of the rectangle is, if we call this A and B, area of the rectangle is just AB. And the length of the diagonal is square root of A squared plus B squared. So to get, so we're trying to get from A squared plus B squared to AB. So first of all, we can square this. We can square the diagonal. We get A squared plus B squared. And that's, I mean, in the problem they did too. They squared the diagonal. So to get there. Okay. And here we can see that oh, we also have the perimeter is 20 units. So a plus b is equal to 10. So we have a plus b, we have a squared plus b squared, and we have ab. So this should instantly like make you think we need to square this. Because if we square this, we get a squared plus b squared plus 2ab equals 100. So this is so we're looking for AB here. So AB is equal to, AB will be equal to, if we shift things around a bit, 50 minus A squared plus B squared over 2. And this can be rewritten as 50 minus 1 half A squared plus B squared. And A squared plus B squared is just D squared, right? So we can rewrite this as D squared. So now we basically have our answer. M is equal to 50 and N is equal to 1 half. So if we multiply these two, Mn is equal to 25. And yep, that's the right answer, 25.
Yeah, so like one way you can do it is like, prove it like algebraically, like how Bill did. But I don't know, like another way you can do this, like, like maybe kind of fast, is like it says like, the formula for the area of any rectangle with a perimeter of 20 units is like this, right? So, what you could do is just quickly take like two cases, just, two cases where the sides of the rectangle add up to 10 So, you can take like 5, 5, and 6, 4. And then, you can find the diagonals of those and you can find the area of those. And then, then you just have a system of equation, or you have two equations, and you have two variables m and n. So then you can do that, and I don't know, maybe that is a little bit quicker. But like I'm saying, like, if you instantly see that, then you can like just go for that, right? Because it will work and it can go pretty quickly. But if you also want to solve it the algebraic way, you can also do that if you can do that. But I'm saying, like, you don't have to prove it the whole algebraic way on when you're actually taking the test. So yeah.
Yeah, so that's just like without loss of generality thing. Just assign values and see what works. Okay. Number 27. Circle O has radius 8 units and circle P has radius 2 units. The circles are externally tangent to each other at point Q. Segments TS is tangent to both circles O and circle P at points T and S, respectively. What is the length of segment OS? Express your answer in the simplest radical form. So, I don't have a circle drawing tool, so this is going to be very great. So, circle O, radius 8 units, and circle P has radius 2 units. I'll draw them like this. Circle P, radius 2 units. It's 2. And these circles are externally tangent to each other, point Q. Segment TS. TS will have to go like this. Segments TS are externally tangent to both circles O and P at points T and S, respectively. What is the length of segment OS? So we're looking for this segment right here. So if we connect these, we make a quadrilateral. And we know the side lengths of these is 2 and 8. So something about tangent lines. Tangent lines are perpendicular to the radius that connects to their point of tangency. So this is always perpendicular. So we can actually just like, we're looking for OS. So we only need TS. So we can do this. We can draw like a vertical here. So this is 2, so this is 6. And we know this is 10 because it's 8 plus 2. So this is 10. So 6, 10, and this is a right triangle. So it's basically just a 3, 4, 5 triangle. So this is 8. So now we know TS is equal to 8, and this is 8, and TO is also 8. So OS, and it's a right triangle. So OS would just be 8 square root of 2.
Okay, yeah. So
Yep.
like I feel like the important part here is that, you know, tangent lines onto circles, if you draw the point of tangency to the center of the circle, that line will be, create a right angle. And so if you ever have like geometry problems and you have like tangent lines on circles, one thing you can try doing is, drawing the point of tangencies to the centers of the circles, because then you'll have right angles which you can try and work with. So yeah. And then
Yep. Oops. What? Okay, I think it stopped moving. There we go. Okay. Number 28. If the degree measure of an arc of a circle is increased by 20% and the radius of the circle is increased by 25%, by what percent does the length of the arc increase? So, um, the 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 circumference of the circle is directly proportional to the length of the radius, right? It's 2r pi. Circumference is 2r pi. So it's directly proportional to the radius. So And if the degree measure of an arc, um, if we think about it, the length of an arc, if we put we if we put the degree measured in radians, and that shouldn't be a problem because radians and degrees are also directly proportional, so that shouldn't be a problem. We can put, if we put in radians, the length of an arc can be, if we use r for the radians, the length of an arc is just r, the radians times the radius, right? Austin, is that right?
Yeah, the length of the arc. I mean, you usually don't denote the angle in radians as capital
Right.
R. I
Yeah,
think
that's
that's
my
very
bad.
confusing.
Yeah, that's my bad.
I just put like theta.
Theta,
I
yeah,
usually
theta,
say like
theta r.
the length of the arc is R times
Yeah,
theta,
r theta.
and theta
I think
is
that's
in
normal.
radians.
Yeah, theta in radians. So, this is the length of the arc. And so we can see that both of these are directly proportional to the length of the arc. So if one is increased by 20%, one is increased by 25%, the final increase would just be 1.2 times 1.25. And so that gives us um 1.5, I think.
Yeah.
Yeah, 1.5. So the final increase will be 50%.
So
And that's our answer,
I mean,
28.
yeah, basically radians are like defined as where like if you multiply the angle in radians by the radius, then you'll get the length of the arc. If you don't know radians, you should definitely get to know it because radians are a very useful tool, and I don't know, like just a general thing to know. Yeah, and also you should know that you should know the formula that the radius times the radian measure of an angle will equal the length of the arc.
Right. Radiance is very important. Okay. So okay, let's look at number 29. In pentagon ABCDE, BC equals CD equals DE equals 2 units. Angle E is a right angle and measure of angle B equals measure of angle C equals measure of angle D equals 135 degrees. The length of a segment AE can be expressed in simplest radical form as A plus 2 square root of B units. What is the value of A plus B? So when you're drawing a graph like this, it's very important to note that, like, to make the graph like good. Like generally, it doesn't have to be that good, but if we look at the units here, if we look at the angle measure here, it's 135 degrees. 135 is a special angle. 135 is just 180 minus 45. So basically, when you're making that angle, let's just draw it real quick. It's basically just like so put B here, C here, and then I guess you can put D over there. Okay, so B would be basically just like this and this. C will be like this, and D will be here. And BC equals CD, so we're going to extend this like this. D. And D, angle D is also 135. So if you think about it, this is 45. If we do another 135 turn, it'll actually be vertical like this. So like this. It'll be vertical now. So it will kind of look like this. E will be here. These are also 2. So, and now it says that angle E is the right angle. So it'll sort of look something like, get rid of this, we'll be extending B like really far. Angle E is a right angle, so it'll kind of look like, oh wow, do I have enough? Yeah, I do. This. So that's what it'll look like. This is here. And if we think about it, this is, I think 135. This is 135. This is 135. The total angle measure of a pentagon is how much? That's 540 degrees, I think. Yeah, 540 degrees. So these add up to these would add up to these add up to 270, and that's 40 405, and that's 495. So these add up, these four angles add up to 495 degrees. So which means this angle is actually 45 degrees. So actually a bunch of nice angles here. So now now we are looking for the length of AE. So this length right here. So to find this length, we can kind of just like split this up like this, I guess. So we know that this length will be just 2 and then plus square root of 2, because this is basically a 45, 90 degrees triangle. So this will be square root of 2. This is also square root of 2. So this part is 2 square root of 2. And because this is a 45, this is, because we dropped a vertical here, this is also 45. So this is a 45, 45, 90 triangle. So this is isosceles. So this side length is equal to this length. We can also find this length, which is also just happens to be 2 plus square root of 2. 2 plus square root of 2. And so if we add both of these, we get 4 plus 2 square root of 2. So A equals 4, B equals 2. A plus B equals 6. And that's our answer, 6.
Yeah. So if you're looking at the sum of the internal angles of a polygon, there's a formula for that. So if you say like the polygon has number of sides n, then the sum of all of its internal angles will always be 180 degrees times n minus 2. Um, do you think you write that, Bill? Um, and it doesn't matter if like um the polygon is regular or not, right? Like obviously our pentagon was not regular in this case. Um, so you can apply this like just whenever. So it doesn't have to be a regular polygon. And this shows up like a lot. In polygon geometry problems, if you ever have like, internal angles and stuff, you can try this out and maybe get some more information. So generally with this problem, it was just like you find like the last angle just with some of the internal angles, and then you just do general geometry. But yeah, so like if you don't know that formula, make sure you know it.
Okay, let's move on to question number 30 now. In triangle ABC, AB equals 12 units and AC equals 9 units. Point D is on the segment BC, so that BD, the ratio of BD to DC is 2 to 1. If AD equals 6 units, what is the length of segment BC? Express your answers in simplest radical form. Okay, so I'm just gonna draw a generic AB and BC here. I'm not gonna draw them. I'm not gonna draw the angle perfectly, or the scale apparently. I'm not gonna draw the scale good either. But AB, AC, 12, 9, and BC, and we're gonna draw D in here. D just like here. This is 6, and um we'll call BC x, and BD will be 2x. So To solve this problem, we'll use something called Stewart's theorem. Stewart's theorem states that for a triangle like this, if we have a triangle like this and it's split by a line like this, if we name each of these length like B, C, name the entire length A, M, and D, we can find a relation between these. And a quick way to remember this relation is DAD, so DAD plus man, 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 M times A times N equals BOM, BMB plus sync, CNC. So this is Stewart's theorem, and like this is the way to remember, I guess. If you have a dad and a man together, they'll put a bomb in the sink. So this might be kind of hard to remember, especially like the lettering part, like how to name it. I generally just remember it as like the dad and man part deals with A, and B is like multiplied to the other side. So BMB and CNC. These are multiplied to the other side. So now we can apply this to this problem. So we do DAD, which is DAD, so 36 times 3x, so that's 108x plus x plus man, which is MA, so this will be 6x cubed equals 162x plus 144x. So now we can take an x out of everything. 108 plus 6x squared equals 162 plus 144. We do some moving around. We get 6x squared is equal 6x squared is equal to 198. X squared is equal to 33. And x is equal to square root of 33. So we're looking for length of segment BC. So BC, and BC is 3x. BC is 2x plus x, so 3x. So 3 times square root of 33 is 3 square root of 33. And that's our answer. Yep.
Um, it's called Stewart's theorem, I think.
Yes, Stewart's theorem. I don't.
Yeah,
Did I say it
you
right?
can search that up and you can find it on like
Yeah.
AOPS. I think probably also the AOPS like um either volume 1 or volume 2 goes over as well, probably. But generally, so like if you have a triangle and like its side lengths and you specifically see like like a line going through it and it divides a side into also like two lengths, then that's when you can apply Stewart's theorem. But yeah, so just generally like another theorem to know for geometry. Yeah.
Yep. Okay. That's all of 2011 National Sprint.
Yes.
Do you want to do 2011 Target next?
Are you asking me or Ishan?
I mean, I don't. I'm not sure who I'm asking.
You're not sure who you're asking.
Yeah.
I mean, we usually move on to targets, but
We
if
usually
if
do.
Lishan
Yep.
wants to do if Lishan wants to do something else, we can also, I guess, do something else. Okay, he said we can do just target.
Okay. Let me pull it up. Or do you want to do it, Austin?
Um, I can do it. I'll have to set my stuff up though.
Okay. Oh, that's fine. I can just do it. Oh man, I have to pull it back up. I think I closed the page. Give me a second.
Wait, did he say for me to do it or for you to do it?
No, I'll do it. It's fine.
Okay.
I just have to
Uh,
pull up the page. "2011 Target." Okay, so I guess let's get started. Number one, triangle ABC, measure of A equals 60 degrees, measure of B equals 70 degrees, and the bisector of B and C intersect at point D. What is the degree measure of BDC? Okay, so triangle ABC. Oh, this isn't gonna be a good graph either, but we're gonna make do. A, B, C. This is 60. This is 70. And the angle bisectors these. So like this and like this. That's kind of it. Sorry, D, and we're looking for the degree measure of BDC. So this is pretty easy because these are angle bisectors, so it's like 30. This is 35. So we just do 180 minus 30 minus 35, and we get 115 degrees. And oh,
wait.
wait, did I mess up?
Um, okay, well, it's bisectors of B and C,
Oh, my bad, B and C.
but also it wants BDC, not
That's my bad, I'm
BDA.
sorry. I kind of got ahead of myself there.
But yeah, it is very easy.
It
I
is
mean,
very easy. Yes.
it's just angle chasing, but like you can just get the angles from angle bisectors.
Right.
Uh,
So this is
so
60,
it's,
that's
I mean,
70,
it's
that's
really just knowing like
50.
angle bisectors bisect an
So
angle.
25, 35, 120. Yep. Okay. That was fairly easy. Number two, the expression. Oh wow, that's kind of small. It doesn't give it much clearer. The expression 2 to the 2010 plus 2 to the 2008 is equivalent over 2 to the 2005 minus 2 to the 2003 is equivalent to what common fraction? Okay. So, oh
So,
my goodness. Okay. 2 to the
you
2010. You can like factor out a bunch
can,
of 2s.
yeah, you can factor out powers of two, a lot of powers of two.
You can factor out 2 to the 2003 out of both of these, and they also cancel out, so you'll be left with 2 to the 7 plus 2 to the 5 over 2 to the 2 minus 1. So at this point, these are like solvable, I guess. You can just like
Yeah,
you can just
and
build things.
there's
This is
also like nothing else to really do. So
yeah.
yeah.
There's nothing else to do. 32 over 3. You get 160 over 3. And yep, that's your answer. 160 over 3. Okay. Number 3. When all of the factors of 90 are multiplied together, the product can be expressed as 90 to the power of k. What is the value of k? Okay, so we can think of it like this. For every factor of 90, there is a corresponding factor that when you multiply those two together, you get 90, right? So like it will be split evenly half and half, right? Like this, these two will correspond, these two will correspond. So like, say like
Well, I mean,
one,
unless 90 was a perfect
yeah,
square.
unless 90 was a perfect square, but 90 isn't a perfect square. So we get 2 and 45 and 3 and 30 and so on and so forth. So we basically just have to look for the number of factors of 90 and then divide that by 2. So to find the number of factors of 90, we can just find the prime factorization of 90. It's 2 times 3 squared times 5. Yep. So to find how many factors there are in 90, every factor is basically like you're choosing how many of 2, 3s, and 5s go in there. So you can either have 0 or 1, 2. You can have, for 3, you can have 0, 1, or 2. For 5, you can have 0 or 1. So you end up, so the number of factors is how many combinations you can make, which is 2 times 3 times 2. You end up with
Yeah, so
12.
factors of a number,
Mhm.
it's just like, in the prime factorization of the factor, the it just has to be equal or less than to the prime factorization of the of the bigger number that you're looking at. And then so yeah, it's just like then you're choosing you're just choosing it like that. So then you can just count like the number of factors like you're choosing it like that. Yeah.
Right. So we have 12 factors, and we have 12 factors, and like we said before, we'll just divide this by 2, so 6, and so k will be equal to 6. And yep, that's the right answer, 6. Number 4, the population of the town of Euler. Euler. Sorry, Euler. That's how you say it, right?
Sure.
Okay, there we go.
Yeah, it doesn't really matter,
Euler
but yeah.
is growing at a rate of 3. It does matter. He's an important mathematician.
Euler. Okay.
At a rate of 3% per year. If the population is currently 35,000, after how many whole years will the population first exceed 50,000? So, this is a problem you'll probably need a calculator on. Let me get mine real quick. Okay, I have a calculator. I got the calculator. Okay. So, um, we're looking for 1.03. So 35,000 times 1.03 to the power of something. So let's just say n is greater than 50,000.
Right. So like every year, the population is growing by 3%. That's saying like every year it's like you're multiplying the population by 1.03. So, you can model your population as your initial population, 35,000 times 1.03 to the power of n, where n is the number of years, right? So that's how many times you want to multiply 1.03. The number of years. Sorry, the number of years is how many times you want to multiply 1.03. And then yeah, you just want to look for that when that first exceeds 50,000. So, then you have that equation, and then you can just solve that equation.
Right. You can just solve this equation. N is greater than
Or it's an inequality, not an
inequality,
equation.
right? Inequality. So greater than it could be just equal to 50 over
It could
35.
No, it says first exceed 50,000.
Exceed.
Can't
Okay.
be equal.
Okay. Exceed. It can be equal to. Okay. So 50 over 35. And what? So now we just have to use logarithms. So like log 1.03. Did I do this right?
Yeah,
Okay.
well, you would have that n is less, well, n is greater than that.
Yeah, n is
Um,
greater than this, basically. Yeah.
yeah, you kind of smushed that on the left there.
Well, too bad. It's how it is. So we can just find this, I guess. And it's looking for whole years. So we can just put this in a calculator. Log 1.03, 50 over 35. It's 12.0 something, 12.06 something. Doesn't matter. It's greater than 12, and we're looking for the first whole year. So n will have to be equal to 13. Yep, 13 years. Square ABCD is inscribed in a circle with diameter BD of length 2 units. Segment AB is the diameter of the half circle on top of the square. What is the area of the shaded region in square units? Express your answer as a common fraction. Ooh, okay. So, I'm just gonna do this. Yay. Okay, we have ABCD here. This thing here. Come on. Okay. So, this is, the diameter is 2. So, we know this is what? Actually, we don't really know that. So here's the origin. So if we look at the smaller thing first, the smaller what is it? I forgot what it was called. Semicircle?
What? What?
Like this part.
You mean that
What's that? What's
that's
the word for it?
sector,
Sec.
right?
What? I don't know. Like the entire thing.
Pretty sure it's called sector.
Okay, we're just gonna call it sector.
Circular sector.
The first sector.
Yeah, it's called a
The
sector.
first sector. So if the diameter is 2, the radius is 1. So also this will be a right angle because it's just diagonal back of a square, so this will be a right angle. So the area of this is 1. The area of the triangle is 1. The area of the triangle is 1. And the area of this sector AOB, will be like the area of the circle is just pi, right? 1 squared pi, so just pi, and this is 1/4 pi because it's a right angle right here. 1/4 pi. So 1/4 pi minus 1. So this part is 1/4 pi minus 1.
Yeah, so the area of the sector is gonna be the area of the circle times the fraction that your angle is of the entire angle of the circle, which is 360. So, the area of the circle is gonna be pi times 90 over 360. But 90 over 360 is just 1/4. So yeah, then it's 1/4 pi.
Yeah, 1/4 pi, and then minus. Oh, sorry, this wouldn't be 1. This would be 1/2 because triangles.
Yes, triangles.
Triangles. 1 times 1 divided by 2. It's triangles. Okay. So now we look for the bigger semicircle up here. So because the diagonal of this square, my bad, square is 2. The side length of it will be square root of 2. Is that right? Yeah, square root of 2. Square root of 2. So hmm?
Yeah, it would be 2 over square root of 2, and then you can just rationalize that. Or you can just think,
Yeah, 2 over square. Yeah.
we can just think like square root of 2 times square root of 2 is 2. Yeah.
And so the area of the bigger semicircle here is like this thing right here. Area of this thing will be square root of 2 over 2, that's the radius, squared times pi over 2. So that ends up with pi over 4. No, it's pi over 4. So AB, this big thing, is pi over 4. So 1/4 pi. Minus, so now we just have to subtract it from this part right here. Minus 1/4 pi minus 1. So these two actually cancel out, so we just left with 1 as our answer. 1 square unit. Did we mess up? Oh, wait. Yeah, this should be 1/2, not 1. I forgot to change
you
it.
said it was 1/2. Yeah.
I forgot to change it. So our answer will be 1/2. And yeah, that's the answer. Okay. Oh, it's 8 p.m. by the way. Do you want to keep going because we started kind of late, or
Are you asking me?
yeah?
I mean, we can stop now. I mean, all right, I guess it's up to you, but I mean, we could just stop now.
Okay. So you want to end it off?
Huh?
You want to end it off?
Yeah. Oh, okay. Um, thank you for coming to this week's meeting. We will pick up from where we left off. Next week we are on 2011 National Sprint, or sorry, targets. But anyway, thank you for coming, and we will see you later. Goodbye.
Bye.